Next we have Malcolm Cowe. I was about to say Cowe. I told you Cowe, and you told me Cowe. Malcolm Cowe from Intel. He's a product manager in Intel's High Performance Data Division, working primarily with Intel Enterprise Edition for Lustre. Malcolm joined Intel HPDD in late 2012 as the Lustre pre-sales solution architect for the Asia Pacific region, and also has contributed documentation to excuse me, Intel EE Lustre, including user guides on CTDB and Samba and HSM. Malcolm has 20 years experience as a system administrator, test engineer, and in professional services. He is also a DC Comics fan, but I won't hold that against him. I'm a Marvel guy myself. Malcolm, please. Thank you, sir.
Thank you. So the purpose of my talk today is to try and describe some of the requirements, feature requests that we're seeing for Lustre when it's applied to enterprise computing or commercial HPC environments. So we're seeing in enterprise a much greater uptake in HPC infrastructure, HPC applications. We're also seeing a need for much more performant, scalable storage. Sites are now rapidly outgrowing their existing infrastructure, their dependence on NFS. They're seeing scalability limits in their infrastructure in that respect. And so Lustre is a logical choice for consideration in these environments. So while Lustre brings a lot to the table in terms of performance and scalability, there's also a need to recognize that enterprise shops are rather more risk-averse, rather more conservative, and they need to have some reassurances around operational continuity for their businesses. So that means recognizing that we're deploying Lustre, deploying HPC infrastructure into environments that have mission-critical, business-critical workloads. That means that there's a measurable cost associated with downtime, that there's an immediate impact to data loss and loss of service. So Lustre's always been really good at the big numbers, right? It's an extremely performant, extremely scalable file system. But we see these new challenges coming in as we try to put Lustre into new IT domains. We see different requirements around performance, different requirements around reliability, availability, and serviceability. We're seeing requirements around security and so on as well. So it's not just about massive streaming I/O. We're not just checkpointing RAM anymore. And we're not dealing with scratch. These are production file systems, and production file systems bring in other problems. So I want to have a look at some of the issues, well, rather look at some of the potential solutions that Lustre can bring to bear for some of these issues. I chose a small subsection of sort of enterprise verticals, markets that are running business critical and often mission critical workloads. But I chose these particular examples because they're also running HPC. So these are all fairly familiar markets for Lustre or certainly for HPC infrastructure. But they do have additional demands, additional requirements as you start to look at predicting and preserving and delivering production data. So life sciences is quite a mixed bag of workloads, but there is a prevalent small file dominant workload, large numbers of very small files being generated at very high rates. There's also a need in here for an increased emphasis on securing data, particularly if you look at healthcare industry. They have heavy requirements around protecting personally identifiable information. And weather and climate, reliability is the critical dimension here. Performance is obviously needed. They're running numerical weather prediction, climate modeling, disaster event modeling codes. So they need performance, they need the results to be very quickly available, but they can't afford to lose that data, and they can't afford for their infrastructure to be offline. I spent several years working at the Australian Bureau of Meteorology supporting their operational NWP supercomputer. It's a resource of national and regional significance. It's not just about getting the weather report out to the TV stations, it's about delivering those services to the armed forces, to emergency services, and also being able to do things like disaster event modeling. So Australian Bureau of Meteorology does modeling around bushfires, which are a perennial problem across Australia. You get fire fronts that can be hundreds of kilometers across, and trying to anticipate where those fires are going to go next, how the weather will affect the direction and movement of those fires is absolutely critical. We also see there's a similar modeling for tsunami events. So again, regional significance. Manufacturing reliability again is pretty key here, but we're also seeing across media manufacturing and electronic design automation, small file dominant workloads being prevalent here as well. In these environments, downtime is loss of productivity. In manufacturing, it's loss of revenue. So it's significant impacts to these industries. They need to have their data available, need to have their file systems available, need to have their applications and workloads running. And financial services has pretty much all the requirements in one. You know, it's small file dominant workloads, highly reliable reliability requirements, and a need to secure and protect information. So looking at the small file problem first, several things that we can be doing with Lustre to try and address scalability in small files. And one of them is looking at client performance. So there's some work underway to look at improving the multi-threading performance of the Lustre client in terms of metadata, get that scalability in the metadata on a per client basis, allow your applications to transact more IOPS intensive I/O more quickly, especially when you're dealing with these workloads that just create thousands to millions of small files per run. And sort of continuing the theme, if we're solving for one client and one metadata target, we might as well, introduce multiple metadata targets as well. So distributed namespace allows us to scale the performance of the metadata servers linearly, particularly when you look at the directory striping option, where you get linear scalability in your metadata. This allows us to dramatically increase the addressable namespace, so we can deal with billions of inodes quite comfortably. But you'll also be able to disperse all of your IOPS intensive I/O across multiple metadata targets. Allows you to get much more scalability in terms of the client performance, and then it also service more clients simultaneously as well. To close out on the small file issue, there's a project called Data on Metadata, or Data on MDT. And the idea here is that for small files, rather than having to create an inode on the metadata server and then go out and create objects on the object storage servers, you can actually do all of that, co-locate the small file with its inode on the same metadata target, on the same metadata service. It affords you a net reduction in round trips. You've got fewer RPC calls going on, fewer transactions to enact, and therefore you get reduced latency. And you should get a net increase in performance here as well. When you couple that with distributed namespace, then we get linear scalability in our small file performance as well. So with the small file performance scalability plus distributed namespace plus this data on MDT, we see a real potential for significant improvement in solving the small file problem fairly holistically. And you combine that with optimizations in hardware. If you're sending your metadata and your small file data out to a very specific set of hardware, then you can tune that hardware, optimize that hardware for the IOs that you're trying to transact. So if you look at putting SSDs, NVMe onto your metadata targets, they are ideally suited for IOPS intensive, small file dominant workloads. So we're now directing at a very coarse grained level IO based on characteristics of the files. That means that metadata servers, they take care of all the small stuff, and we still have the object storage servers for all the large stuff. And we get linear scalability across both of those services with striping. And layout enhancement is a foundational project. Allows us to start to look at options beyond just striping files. So we're able to, with layout enhancement, describe different types of file layouts depending on different requirements of the customer or the user. And progressive file layout is a way of providing some automatic policies about the layout of files. So going beyond having to do everything by hand, having your users having to have a very specific education on how to lay out their files depending on their workload characteristics, trying to avoid the holes where a 1 kilobyte file is striped across 100 OSTs, and then the inverse of that, where 1 terabyte file is not striped at all. Progressive layout provides a way to automatically lay out the file based on its size. So you can start out with a single stripe for a very small file, and then as the file grows, as you write more data to it, it can be automatically restriped to try and balance out the work. The interesting aspect of layout enhancement for me, coming from a sort of enterprise computing background, is fault tolerance. The opportunity to describe a file layout for your data that improves the reliability at a Lustre level. So with layout enhancement and file-based mirroring, we're able to replicate the data across multiple OSTs within the file system namespace and have that specifically described inside your metadata inside your inode. So you automatically get the replication layout. This means that one of your OSTs fails, your data is actually protected, and it's available automatically and immediately from another OST. This has a lot of implications in terms of data availability and the overall reliability of the file system in terms of meeting service level agreements, improving the sort of multiple nines uptime. Because with the model we have today, we're reliant on pacemaker core sync or HA infrastructure of some sort to recover from server failure. We're reliant upon OST recovery. If an OST goes offline, it has to either be remounted somewhere else or it has to some other way be brought back online before the data on that target can be recovered and be reutilized. Now, if everything's working smoothly, that can happen in a few seconds to a few minutes. It's usually a few minutes in terms of failover. That's enough to cause you to miss your service levels on a mission-critical platform. With the replication, you no longer have to wait for that OST to recover. So the client will be immediately aware that their data is available from multiple targets. If the first target doesn't respond, go to the second target, your data comes back. That's milliseconds turnaround. So the implications here are pretty huge. I don't think that we'll ever get rid of things like pacemaker. There's still going to be a need for striping. There's still going to be a need for performant layouts versus availability layouts. But the possibilities here in terms of improved serviceability and improved availability of your data within HPC or within your application space, and as far as the clients are concerned, is pretty tremendous. The second part of fault tolerance is one that's actually not strictly speaking a Lustre problem. It's a problem of any scalable storage platform. That is one of replication to a secondary storage target. This is a big enough problem today with enterprise computing environments with terabytes of data, but we're seeing default deployments now are going out at least a petabyte, going up to 5 petabytes easily into enterprise environments and a lot of sort of mid-range HPC environments. But you're dealing with production data if you're working in enterprise computing or commercial HPC or life sciences or any of these verticals. And if it's production data, it has to be protected. Going out to recover data takes too long, and so online replication is the typical means to help with disaster recovery scenarios. And that means that you've got 2 online file systems, typically, usually in different data centers. You have a primary and a secondary. If the primary site goes offline, you get your data back from your secondary. And again, failover has to be very quick for that kind of thing to happen. There's no tools for this, right? The typical tools still used today is rsync. And it just doesn't scale. So we need to look at how we solve for that with user space tools that complement the scalability that we get out of Lustre. With the introduction of ZFS as a backing store, we've been looking at some of the features of ZFS itself. And we'd like to incorporate a snapshot functionality into Lustre. Again, this is a feature that is commonplace in enterprise data centers. Guys that have been using NAS filers, scale-out storage for the last 10, 15 years, they've been using snapshots in some way or other. And it's available in a lot of RAID arrays and controllers as well. ZFS has this feature. We reckon that we can exploit this feature in Lustre to create a consistent snapshot across the file system, and then mount that as a separate volume. And this is very helpful for your kind of layer 8 problems, quick undos, and rollbacks in case you've lost some data. The last thing I want to talk about today is security. There is an increasing demand for protection of data. If you look at life sciences, particularly the healthcare industry, it's heavily regulated for personally identifiable information. Protected health information is a regulated part of the healthcare industry, and they need to have some assurances around security. You see a similar requirement coming out of government agencies, particularly defense, but other government agencies as well. And in manufacturing industries, particularly ones with anything that's commercially sensitive, or who are again working with maybe government defense contracts. They all need to have some means by which they can secure access to the data, provide encryption to that data. Just looking at the financial costs, there's a real measurable actual cost to theft of data. The healthcare industry is front of mind with several recent high-profile breaches. The average cost of a single incident in 2013 was about $3.5 million in immediate costs for data theft or data intrusion in healthcare businesses. The ongoing costs can be much more significant. You get loss of credibility, loss of revenue. You open yourself up to litigation. It's extremely problematic. So one of the ways that we can address this in Lustre is to look at SE Linux. SE Linux is a feature that's been in the Linux kernel for a long time, developed by the NSA originally, and it provides you with a feature called mandatory access control. And this means that your operating system enforces permissions policies, access policies, and the user doesn't actually have a say in overriding those. You also get role-based access control as well, and you get a little feature called multi-level security, which is allowing you to give your intellectual property different levels of clearance. Encryption is the other piece that we need to solve for. There's 2 parts to this: encryption of your network traffic. And it's very encouraging to see that there are actually 2 projects underway that are attempting to solve this problem in Lustre. One is the shared key cryptography from Indiana Uni. And we have Kerberos Revival largely being developed by Boole. And actually we'll be hearing about more of this in the conference. So I don't want to say too much about this other than to say that it's extremely encouraging to see these kinds of fundamental protocol changes being available in Lustre for us all to be able to consume and use and employ for whatever needs we need. And then we have encryption of data at rest, and this actually is something that we can solve outside of Lustre if we choose to. We can use de-encrypt with Lux, and don't have to actually do anything at Lustre to fix that. The biggest issues around encryption are around key management. So that's really the unsolved problem with respect to, particularly with the data at rest. But any time with encryption, you've got key management issues, and you have a distributed file system with potentially dozens to hundreds of servers, hundreds to thousands of LUNs. It could be an interesting challenge to solve for. So that deals mostly with Lustre stuff. I've tried to keep the talk mostly around the Lustre file system. There's a lot that we can be doing in user space as well. Data management is really the endemic problem, the hardest problem to solve for when we look at enterprise computing. Working on things like data movers to replicate data between file systems. Looking at HSM and the user space tools that are needed to make HSM an actual viable, let's call it, product. Lending support to projects like Robinhood is extremely important to building out our ecosystem in terms of a Lustre file system that is commercially viable, is relevant across as many storage conversations as we can possibly have. The Lustre community does really well at innovating in storage. It's a very mature community, must continue to drive innovation in HPC storage to remain relevant. That's really the takeaway. We're doing a lot of great work here. I'd like to see that continue. I'd love to see this community grow and incorporate more and more users and give us more and more perspective and more things to innovate on in the future. Thank you.